Hey.
Hi.
Hi, how are you?
Good, how are you?
I'm good.
All right. Let's see. Blueprint. Do you want me to share screen or do you have the questions?
Yeah, I put them in the OneNote notebook.
Right. Yeah, I do see that. Okay. We can start with question 6, I guess.
Okay. The ones that I wrote. Oh, okay. So the first one, or rather, question six.
Mhm.
Um, so a lot of times they're going to make you do or tell you to do like some kinematics
Yeah.
stuff, but a lot of times you can answer those questions using conservation of energy.
Mm-hmm.
So, a really good formula to memorize is what I wrote. I wrote V final is equal to the square root of 2 GH. Do you know how I got that?
Well, like how this equation
Yeah.
came to be? No, I just know it's like one of the ones that you use.
Yeah. So it's the complete conversion of potential energy into kinetic energy. So, um, I'm gonna write some stuff down. Unfortunately, there's gonna be like a delay. Well, okay, you know what? I'll write it in the whiteboard, and then you can see it as I write it. And then I guess I'll copy and paste it onto the notebook. Here, can you let me
Oh,
share my screen?
yeah. Okay, hold on. Okay.
Okay, so this is the complete conversion of potential energy into kinetic energy. So total energy, right, is going to be the initial kinetic energy plus the initial um, gravitational potential energy. And
Mm-hmm.
since energy is conserved, it's also going to be equal to the sum of the final kinetic energy and the final potential energy.
Mm-hmm.
Now, so okay, what's the formula for kinetic energy?
Half mv squared.
Good. And you see what I'm writing on the whiteboard, right?
Yeah. Yes.
Okay, so I'll write 1/2 times mv. That's supposed to be like an initial like subscript, like an I.
Mm-hmm.
Um, and potential energy.
mgh.
Good. I'll put like height initial, I guess, is equal to 1/2 mv final squared plus mgh final.
Mm-hmm.
All right. Now, right away, what can we cross out?
From based on the question.
Oh, just based on the equation.
Oh. We can cross out final potential energy.
Well, Okay, first we can cross out just from the equation itself, like had nothing to do with the
Oh,
question.
oh, oh. M.
Good. So the m is gone, right?
Mhm.
Okay. So um so okay, let's say we want to find, so let's say it's something that is like totally potential energy at first and then gets completely converted into kinetic energy. So let's say that the initial kinetic energy is 0,
Mhm.
and so all of the initial energy is in the potential energy,
Mhm.
and since it gets completely converted into kinetic, the final potential energy will be 0.
Mhm.
So then we'll just have um, basically GH is equal to 1/2 V final squared. Now, tell me what to do to solve for V final.
You like how to manipulate this?
Yes.
Oh, times 2
Good.
and then square root.
Good. So that right there is how you uh, that right there is basically like such a useful thing to use, because you can use it, like I've used it so many times on questions where they tell you to use like all this kinematic stuff, and it's just not necessary because you can just use this formula. So this is what I think is much more useful to have memorized than, honestly, than the kinematics equation that they tell you to use with the v squared blah blah blah.
Mhm.
So a lot of times you can just use that. So
Yeah.
in this
I
case,
have seen it in like questions where they ask you about like drilling a hole in a
like
like
a
container.
water tank.
Yeah, yeah, yeah. That
Yeah,
one.
yeah. So you can
Mhm.
use it for that, since when it's before the hole is cut, the water is just steady at a specific height, and once you like cut up like put a hole in it, or if it's like coming out of a spigot or something, it gets just converted. All of that gets converted into kinetic energy, aka velocity. So yeah, for this question, they're saying that suppose a moderately hard surface, such as the hard packed earth described in the passage, is found to decelerate a person, making a feet first landing to a stop in an average of 0.09 seconds. Also, there are some math like fractions that I think are very useful to memorize as well. Like 0.09 is 1 over 11.
Mhm.
So I think it's useful to memorize like 1 over 7 also, that's 0.143. Um, you know, 1 over 11, oh, sorry, 1 over 9 is 0.11. Um, and also a really good one is 1 over 12, which is like basically like 0.083, which happens to be the ideal gas constant if you're using like I think liters times ATM. So whenever
Interesting.
you can,
Okay.
use fractions, because that makes the math so much easier.
Yeah. I usually go for like the 1/4, like the basic ones. I
Mm-hmm.
haven't thought of these ones, but okay.
Yeah, and then there's another trick here that like is also like one of my special tricks. I remember talking to like one of my friends who's like really good at math, and he was telling me it's impossible to be able to figure out the square root of a number that's not a perfect square. And I spent like a entire like subway trip thinking about it, and then I figured it out. And so I'll show you that as well. So anyway, um,
Mm.
so we basically have the height, which is 2 meters, right? The time, which is 0.09 seconds, which is 1 over 11 seconds.
Mm-hmm.
And they're asking for the acceleration, which is just the change in velocity over time, right?
Mm-hmm.
So, first thing I do is I use that equation to find the final velocity. So that's, I'm obviously not going to use 9.81. So I'm just going to use 10 for g.
Mm-hmm.
So just 2 times 10 times 2, which is
Yep.
40. And now this is where my trick comes in. I mean, I'm sure that's enough for you to be able to get the answer. But if you, really wanted to be, super precise and find out the square root of any number that's not a perfect square, you would just do this. So I wrote, a perfect square that's underneath, or that's less than 40, so 36. Radical
Mm-hmm.
36 is 6, right? One that's
Yeah.
greater than 40, which is 49, which is, and
Mm-hmm.
radical 49 is 7, right? So it must
Mm-hmm.
be between 6 and 7,
Mm-hmm.
but you can actually, know exactly, how much it is in between 6 and 7, because 36 to get to 40 needs to go up by 4, and then the total, um, numerical distance between 36 and 49 is 13.
Mm-hmm.
So it's just 6 and 4/13.
Wow.
Yeah.
Does it
And
work every
4/13, 4 over 12 is 1 over 3, which is 0.33, right? Repeating.
Mm-hmm.
6.33 repeating. But since 13 is, slightly larger than 12, I'm going to just take that 0.33 part and make it slightly smaller to get 0.31.
Interesting. Okay, I will go test it. Does it work every time like this?
Yep. Yeah, give me any other number. Well, not
That's
a crazy one, but yeah, generally speaking, yeah, yeah, it works.
that's cool. Wow. No, that's really cool. I just know it's like between the number, but I never
Mm-hmm.
really. I
Yeah.
kind of take like the halfway point and then just kind of
Yep.
like
Yeah, yeah, yeah. Yeah, yeah.
estimate.
Like I said, I spent a subway trip just thinking about it, because I wanted to prove my friend that it was possible. Um,
Right.
but yeah, so you get 6.31. I put the curvy equal sign. So
Yeah.
that's that, and then acceleration is delta v over delta t. So you know I get this, and then I just multiply it by the reciprocal of 1 over 11, which is 11. So you get roughly 70, right?
Mm-hmm.
Which is basically 7 G's.
Yeah.
Yeah.
So, so how do I know that the equation that we derived works for this case?
Because this case, it's the complete conversion, because the guy is falling from a height of 2 meters, right? So when he's 2 meters above the ground, he's not moving, so he's all potential energy.
Mm-hmm.
When he hits the ground, um, there's no more potential energy. So he's going to have all of that converted into kinetic.
Okay, that makes sense.
Yeah,
Okay.
we're going to use oh yeah, yeah. So that's how you do that problem.
Okay. Yeah, no, it's way easier than what they have in
Yeah, their entire woo, this is a fairly heavy question. Might be one to
yeah.
skip over, and then but it's a lot easier than that.
Mm. Okay. Sounds good. Let's see. Okay. Child is accidentally pushed.
Yeah, so this child one, so all right, some pushed directly forward off of a ledge, and they give us the kinetic energy, and we just have to find his or her velocity. So this it's 720 joules is equal to 1/2 mv squared. We know it's 40 kilograms. So you just rearrange that and solve for velocity. And I get 2 times. So okay, so how I did this math, so I wrote 2 times 720 over 40, right?
Mm-hmm.
And so the first thing I do is I notice a 0 over here and here.
Yeah.
So I cross those out. All right. Then I notice a 2 up here can go into the 4 here. So the 2 crosses out and the 4 crosses out to get a 2 down there.
Mm-hmm.
And then 2 goes into 72. So, 2 goes into 7 3 times. There's 1 left. 2 goes into 12. Wait, sorry. Oh, yeah. Okay. So, yeah, 34 is the next one.
Wait, isn't it 36?
Yeah, I just noticed I messed that up. I was like, 2 goes into 12, 4 times. Wait, no. So, yeah, that's supposed to be 36, which is good because it's a perfect square.
Perfect.
I guess I wanted it to not be. So, okay, so, yeah, so you get 6 as the velocity, right? Now that's like the resultant velocity. So I drew this here, like the resultant vector, right?
Mm-hmm.
As v naught, and the vertical component is the resultant times sine of theta. Horizontal is a resultant times cosine of theta. And you should also know like the cosine and sine stuff.
Yeah.
And also that cosine of 0 is equal to sine of 90.
Mm-hmm.
All right, yeah, they kind of go in that way.
Mm-hmm.
So yeah, that's just 1/2. So 1/2 times 6 is 3. So it's 3 meters per second.
Interesting. I just okay. Cosine thing. How is it cosine thing?
What's up? Oh,
why
because
is
it's the
cosine
horizontal component, right? If someone's pushed off of a ledge, right?
Yeah.
You're like you're push. It's a funny question. It's a child being pushed off a ledge, but you're pushing them horizontally, right?
Yes.
Yeah.
Okay. And so is the 6th...
And it says directly forward.
Oh, yeah. So the 6 meter per second is the angle, right, that it comes.
Oh, the 6 meters per second is the total velocity, which is a combination of the velocity from the horizontal velocity of being pushed directly forward, plus the vertical velocity that's from gravity. Well, yeah.
Well, if it's horizontal and vertical, why is it not tangent?
Why is it what?
Why is it not tangent?
Tangent? Because you're never going to have to deal with tangent, and because tangent doesn't really exist. Tangent is just a function of sine and cosine, and sine and cosine are just functions of the unit circle.
Mm-hmm.
Yeah, you're never going to have to do anything with tangent on on this.
That's what I realized.
Yeah.
Okay. All right. Okay. Sounds good. I think I just need more practice on these questions.
Mm-hmm. Yeah, the next up ones are really good practice for calculation heavy types of problems.
Mm-hmm. Okay, let's see. Next question is fracture.
All right, according to the passage, which of the following individuals is least likely to experience a fracture, assuming that all have the same mass and fall onto hard-packed earth from a height of 2 meters? So I'm looking at the passage and okay.
Well, I was able to eliminate B and D based on the passage. Like I just
Oh,
somewhere is that
yeah,
a
if it's
larger.
closer to being perpendicular to the surface, it's
Yeah.
going to be, more in line with the force of gravity and therefore, hits the ground, with all of its energy rather than coming at it at an angle. So, 80 degrees is closer to 90 than 40, so smart to get rid of the ones that are 40 degrees.
Mhm. And then I think the cross section, I think I'm supposed to look at figure one
I see
for that.
that. Okay, in the third paragraph, let's see. So they tried something and they found some relationship between. Okay, but it didn't follow a clear functional relationship. When they mean that, they mean like actually like a function, like a mathematic function. Um,
Mhm.
so okay, when they accounted for the mass of the person injured, as well as the cross sectional area of their bones, a relationship between the applied force per square unit of bone cross section and break frequency was found to be similar to a binomial distribution, as seen here.
Mhm.
So, basically, like, they're basically just saying that, and it makes sense even if you didn't have that figure one, because okay, so in physics, pressure is okay. Tell me what pressure is like. In,
Pressure is force over area.
good. All right, good. So, you know, basically, if you apply a force
Mhm.
over a greater area, the
Mhm.
pressure isn't going to be as high.
Mhm. Yes.
So, if it should follow that if someone's like bones like are just have a greater cross sectional area compared to like smaller bones,
Mhm.
that force, that energy is dissipated over a much larger area. So there's less pressure, and the bone, is able to sustain um, that type of like hit without becoming fractured.
Right. Yeah, yeah. No, that makes sense.
Mm-hmm.
Yeah, yeah. So then based on the figure, because the figure is kind of saying the same thing, right? Because it's the the x-axis is saying force per cross section area.
Mm-hmm.
So then if the cross section area is larger, then the overall pressure will be lower. So then it will be less breaks per injury.
Mm-hmm.
Okay. I just like didn't read the graph properly, I guess. And
I
also
mean, the
didn't
graph doesn't even
think
really
about.
help that much because it's like a sigmoidal curve, and it doesn't. It would only help if you knew that, um, because what they give you is the force per square unit, and then the break frequency,
Mhm.
but it wouldn't help unless you knew that, um, like break frequent. Well, okay, it just tells you that break frequency increases as force per square, centimeter increases,
Mhm.
and force per square centimeters. So okay, where is that here? Oh wait, no. Okay, so force over area, right? Like they're basically saying is proportional to break frequency, right?
Mm-hmm.
Um, so it should mean that break frequency is inversely correlated with the cross-sectional area, right?
Mm-hmm.
So as the cross-sectional area increases, the break frequency decreases. By the way,
Yeah.
tell me what um, a inverse proportion like this would look like on a graph.
Like this way.
Like that?
Yeah.
Okay, so it's actually going to look like this.
Okay.
Now, tell me, why do you think it would look like that?
Wait, what's like the proportion between these?
Yeah, just,
Wait,
an inverse relationship. Let's say this is like um, something like uh,
is it because it's like 1 over area?
yeah, okay. Now, tell me the significance of that.
Um,
What can, if it's 1 over something, what, like 1 over a, what can a never be?
0.
Yes. That's why there's a asymptote down there.
Okay, yeah.
So, it will just infinitely get closer and closer,
Right, right.
but never actually touch it. So, I've seen them ask questions about this before. So, you know, you're never going to see like this straight line going down. It'll be like, like that kind of curve.
Interesting. That's a good reminder.
Mhm.
Yeah. Okay. Um. Okay. Next passage, which is passage 4.
Okay. An experimenter proposed employing a material with an index of refraction strongly dependent upon the wavelength of transmitted light for use in an objective lens. Okay, so objective lens is in a compound microscope where they essentially use two lenses.
Mm-hmm.
And the objective one is, they're saying, okay, the objective lens is a converging lens that's located near the sample being viewed,
Mm-hmm.
to form a real enlarged image of the object inside the microscope. Um, so let me go zoom in on this. Okay, so basically, the objective lens makes a real image. So like, what's the difference between a real image and a virtual image? Like the main difference.
uh, does it have to do with where it's formed, where the image is formed?
Well, so okay, a real image is a real image in that it can be projected onto something. Whereas a
Okay.
virtual image cannot be projected onto anything. Like it's just like within the mirror world. But, a real image will produce a picture. So the objective lens produces an actual image, like a real enlarged image of the object inside of the microscope. And then a second converging lens magnifies it even more.
Okay.
Okay. Now, oh wait, this is like what we talked about before with myopia,
Mm-hmm.
where I talked about eye length.
Yeah.
Oh wait, I skipped
Repeat.
one. Sorry. So, okay, 19. All right, let's see. Index of refraction strongly dependent upon the wavelength of transmitted light for use in an objective lens. How would the use of such a material impact the performance of a microscope? Um, okay, so the main thing here is angle of reflection is always going to be equal to the angle of incidence. Um, if the index of refraction increases, then the angle that it bends at gets closer to the normal, closer to the
Oh yeah.
yeah.
Actually, look, I was gonna ask something. So
Sure.
normal. So I know that if based on like the angle, the index of refraction, it either like goes towards or like away from normal. But what is normal?
So normal is perpendicular to whatever that surface is. So
Perpendicular. Okay.
yeah, so let's say this is the interface between, two different media. Let's say this is like air and this is like water. And this is just, an imaginary line that's perpendicular to that interface.
Okay.
So let's say, this is a light ray, right? Let's say that is, it being reflected. And so this angle, these two are equal. So the angle of incidence is equal to the angle of reflection. Now, if it goes into something that has a higher index of refraction, it's going to bend toward that red line. We call that the normal, which is just the line that's perpendicular. So it's going to bend closer. So let's say this is index of refraction, this is incidence. So, the angle of refraction is going to be less than, the angle of, incidence.
Okay, so normal. So bend towards the normal just means it's gonna go towards the.
Yeah, it's going to go towards, like that imaginary 90-degree, perpendicular line.
Okay, makes sense. I just didn't know where the normal was. So.
Yeah, they there's like a funny like meme that I saw about like physicists coming up with like so many different words that mean like 90 degrees, like 90 degrees, right angle, normal, orthogonal, perpendicular, orthonormal. That's also one. Yeah, but yeah. So that's basically what happens when it enters, like a medium that has a higher index of refraction.
Okay.
Yeah. But the angle of reflection is going to be the same.
Mm-hmm.
So D is out.
Oh, right. Yes, D is out.
Okay.
Sure.
Now, they also try to like trick you by asking about less light or more light.
Yeah.
Now, sometimes they'll ask you like a question that's like, energy like or photons of this frequency or this wavelength, like are bombarding some element or something that causes, its electron to go from a ground state to an excited state. What will happen, and it takes like, let's say it takes like 13, whatever, electron volts for it to happen. And let's say you're shooting it with photons that have 12 electron volts. Like, what can you do to make sure that this thing gets excited? And they would say something like, a choice would be like, shoot more photons.
No, that doesn't change it.
Yeah, so like that is, so like luminosity.
It's related to the intensity of the light, the number.
Well, luminosity is the same thing as brightness, which is the same thing as intensity,
Mm-hmm.
which is the same thing as number of photons.
Mm-hmm. Yeah.
But that wouldn't work in that hypothetical question that I was talking about, because energy, like the frequency of the wavelength, or the frequency is what determines the energy.
Mm-hmm.
So
For
if
sure.
it doesn't have enough energy, shooting more photons isn't going to do a thing.
Mm-hmm.
So that's what they're doing by saying less incident light.
Yeah.
Yeah. Oh, so what they say about velocity of light? So okay, that's actually true. So like, as it goes into this medium, the velocity of light is actually decreasing. So the common, when they say 3 times 10 to the 8th power meters per second, that's the speed of light in a vacuum, like space.
Mm-hmm. Mm-hmm.
But it's like slightly slower in air and, different types of media.
Mm-hmm.
So anyway, so A is out.
Yeah.
Okay, so now we have things going. So we have something that's monochromatic.
Mm-hmm.
So what do you think that means?
So monochromatic just means like one color, which means it will
Yep.
only have one wavelength.
Mm-hmm.
Or that's like what I think.
Yeah. So if it's just one wavelength and the index of refraction is strongly dependent upon that one wavelength, it should still be able to converge to a single point.
What is converging to a single point?
Oh, just like so, converge means going towards, right? Divert, like going towards each other.
Oh.
Diverge means going away from each other. So, if you want to produce an image, right? That's why in the ray diagrams, right, you see all these rays
Mm-hmm.
converging at a single point to produce that image.
Mm-hmm. So, okay. So then because it's just monochromatic, which means the index of refraction will not change, then it should converge to a point. Okay.
Yeah.
Okay. All right.
Now, if it has multiple wavelengths, like, more than one color,
Mm-hmm.
then they're not going to converge at a single point,
Right.
because
Because
they're,
the index of
yeah, they're going to have
convergence.
different angles. Like, you're going to have
Right.
like, like that like image of like a prism, and like white light is hitting it, and then, you have like, all the colors of the rainbow.
Mm-hmm.
Yeah, that's it. That's exactly what happens like that. So, um different wavelengths will have different angles of refraction, and they won't converge at a single point.
Mm-hmm. Yeah, that
So
makes
it'll
sense.
be unfocused.
Okay.
Yeah, and it's called chromatic aberration.
Mm-hmm. Right. I've heard of it. Okay. Makes sense. It's just the wording of this question confused me.
Mm-hmm.
Wording of the answers. Okay.
Yeah, I actually did a like I used to do like cosmology research in physics, and one of the things we researched was this star called Boyajian star. And do you know what exoplanets are?
No, I did not study
Uh huh.
astronomy at all. Like
So
I had
base
no idea.
so basically so the exoplanets are just planets in different solar systems. So we basically just look for like, we look at a star and we measure its like light intensity over time. And, if we see something like this, those little dips in light intensity, brightness, right, indicate that there's something blocking it, right?
Mm-hmm.
And if the dips have, a periodicity, like, like a they happen periodically, like
Mm-hmm.
it would indicate that it's an exoplanet because it has an orbit, right? And but the thing with Boyajian star was that, it had all sorts of weird, kind of things going on. So we were trying to figure out what it was, and we used data from this thing called Kepler. It's like this like probe that we sent out into space to help us find exoplanets. But we were using basically monochromatic like wavelengths. So we just looked at it like as some object that's opaque, and like something like that. But the person who actually discovered the star ended up doing like a Kickstarter and working with like a bunch of observatories around the world, and used multiple wavelengths to find out that it was just like space dust. That just resulted in different wavelengths hitting it and bouncing off in all sorts of directions.
Wow.
So, yep.
That's good. Now I'll remember it more.
Yeah.
Yeah. Nice. Wow,
Yeah.
that's cool.
I was like light stuff thinking about it.
No, that's really cool.
Okay, the next one, yeah, that's so we talked about the myopia, that's nearsightedness. Hyperopia is farsightedness. It just means, your eye is, basically shorter.
Wait, myopia?
Mm-hmm.
I thought myopia was your eyes are longer. Because you're like
Sorry. Because it forms the image in front of the retina, so it's longer. Yeah, my bad.
That's me. I'm extremely myopic.
What's like your do you know like yeah.
I think it's like -5
or
okay. Something. Well, it's not that bad, but I have like astigmatism too, which like makes it worse. So.
Yeah, that's actually like the previous question. What like both of your eyes like have like different focusing like focal points. So the overall image that you make from both of your eyes is like fuzzy. So, but
oh yeah, totally. So this question, what confused me was I couldn't figure out.
It could be what I just said. Where myopic, yeah. But they're just saying normal person or something. Wait.
I guess I was trying to find out what eyes near point meant. And the passage said in the second paragraph that the near point is the closest distance at which the healthy naked eye can focus.
Oh.
So I was like, that doesn't make any sense to me.
Wait, where
it's under
near point, which is the closest distance at which the healthy naked eye can focus. Okay. So I guess if you're nearsighted, the near point, since you can't see things that are far, is going to be closer, right? Or shorter, right? Like that's what they do with like the whatever when you do like the eye test, looking at the chart.
Yeah.
With like the big E on it, like 20/20. So basically, like 20/20. So like is the standard. So, that means that at 20 feet you can see what most people can see at 20 feet. Some people are lucky and have like 20/10 vision, which means that they can see things 20 feet away that most people, the normal people, would need to be 10 feet away to see. And then for us, since we're, myopic, it's like 20/40 or something like that. I don't know. Like we can see things that at 20 feet that most people can see at like 40 feet or something like that.
Hmm.
So that's like kind of like another way of looking at it.
Okay. So how I understood this question is, so it's asking that when compared to a healthy eye, if somebody is myopic, then the near point will be, so near point, how I interpreted was, so since it's the closest distance that the healthy naked eye can focus, and I thought that if you're myopic, then you're focusing way in front of the retina. So then I thought the distance would increase, but
Yeah,
like,
yeah. So I would have thought that too if they talked about the eye's focal point, because myopic people have longer eyes, so the focal point is higher, or larger than that. Focal distance is larger than that of a healthy eye. But since they said the near point is a distance outside of your eye, that it's the closest distance that you can like focus and see something on.
oh, it's like outside of your eye, not
Mm-hmm.
like,
Yep.
oh, okay,
Mm-hmm.
I see. Wait, how did I not read that right? Oh my God.
I mean, like, I didn't either until you mentioned your point, and then I looked at your point.
Distance? Oh, so it's like the distance literally like out, like the distance you can see.
Mm-hmm. Yeah, I think that's called proximal.
No,
Like,
I think it's distal.
oh, okay, okay, yeah, there you
Yeah,
go.
you're talking about that psych term?
Yep, yep, yep,
Yeah, it's distal.
yep.
Distal
So
stimulus
distal,
or
yeah.
something.
Good
Oh God.
job.
Okay, that makes sense. Okay, all right, makes sense. Wow. Um. Okay, next question. Okay, this one's I think is pretty hard.
Yeah, for these, I would just memorize that table.
Mm-hmm.
So, let's see if I can do that. Like, like
Yeah.
when before taking the test, like when you do the tutorial, I write it down like on the like stuff that they give you.
Yeah.
So I have it as reference. So, and usually like obviously like I don't have like photographic memory, but I can like, so okay, let me see. So I know it's like SUV, um, like tiny, um, inverted, real, whoops, smaller, inverted, real, same size, inverted, real, um, no image, and then larger, upright, virtual. And SUV is just for diverging stuff. But for converging stuff, it's going to be these, depending on, the object's like distance. So like if the object distance is like at infinity, it'll produce like a really small uh inverted real image. Um let's say the object distance is, I think, let's see.
Smaller. Wait, smaller inverted. Smaller. Uh, is it like outside of the focal point or something? Oh.
I'm trying to see if I can remember this. So let's see. If the object distance is at infinity, it'll make this. Object distance somewhere. So okay, I don't remember those. So because what is it? The what, like where you remember the primacy and recency effect. So I remember that, And I remember that over there. Yeah.
Oh wait. Oh no, it's called no, it's combined
The
to be called
serial
serial
position effect.
positioning of it. Yeah,
Hmm.
there you go.
Yeah. So okay. This is where the object distance is infinity. Here it's within the focal point or focal length. I think here or this makes the same size one. Um, this could be something like 2f or something like that. Anyway, they're asking you for um, it to be like erect, which is just another word for saying upright.
Hmm.
And if it's upright, it's always going to be virtual, by the way.
Yes.
So the only way that it'll be virtual is that um, it'll be like this, the bottom one,
Mm-hmm.
which means the object distance is within the focal length. That produces a larger upright virtual image.
Okay. Yeah, I see that. Um, a distance from.
Yeah, so I would just memorize like this over here, like, even if you don't memorize like part of it perfectly, you can still like, like figure stuff out if you just kind of like remember like because I write it like this, like diverging stuff always produces a smaller upright virtual image. And then for converging stuff, as the object gets closer, the image gets larger. Like it starts off tiny, then small, then same size, then no image, right? And then it starts to get large, upright, and virtual.
Mm.
So, you could just kind of like, yeah.
Uh,
Mm-hmm.
okay, that's good. Okay, but I think I was confused because this question had like two lenses,
Yeah.
and
So, yeah, for the for two lenses, like don't let it um don't let it psych you out. Like just treat like the objective lens as something that just produces an actual like a real image, and then treat that real image as the object for that second lens.
okay.
Yeah, that's another thing about real images. When I say that they can be projected, I mean that you can treat them as an object.
Uh,
Mm-hmm.
oh, okay. So then, okay, so because it's just another object, then you can just kind of ignore the first ones. Right.
Exactly.
Oh, okay.
Mm-hmm.
Oh, okay. Need to write this down. Okay, makes sense.
Mm-hmm.
Great. Uh, okay, let's see. How many more questions? One, two. Next one is ideal. Okay, I sort of figured it out, I think. Ideal condition.
Okay, yeah. So basically, ideal conditions means that the particles of the gas don't interact with each other, right?
Yeah. Mhm.
So, what conditions can replicate that? So, let's
Yeah.
say two particles, like, meet on a street or something, like, and say hello. You don't want that. So, how
Yeah.
can you make it not happen? Well, you can make them go really fast, which is temperature, right?
Mhm.
Temperature is just average kinetic energy of those particles.
Mhm.
Um, and you can have like the pressure really low, so they're not even gonna like be on the same street.
Right, right. Exactly.
So, we so let's look for something that has um like okay, so they're messing with like they're messing with units. So,
Yeah.
people, yeah, so that's the tricky part about this. So
So
so like so okay. First of all, like 285 Kelvin.
I think I will cross out the answers that had Kelvins
Wait, why?
because Kelvins is low temperature. Like, because you have to minus like 273 to get to Celsius.
Mm-hmm.
So then, because the Celsius already, like C and D already has like really high Celsius temperature
Mm-hmm.
compared to the Kelvin, so I would just cross out the A and B.
Yeah, I'd be careful. Like, don't necessarily cross out something just because it's in Kelvin. Kelvin is the best, you know, unit to use for temperature. Why do you think?
Uh, well, is it because like 0 Kelvins is like the absolute temperature where everything stops moving?
Which means that there's no negatives, right?
Yeah.
So Kelvin is the best thing to use, ultimately speaking. Um. So, so I think it's best to think of things in Kelvin. So, 285 Kelvin is just like 273 plus whatever amount to make it 285, right? That's like 12 or something, right?
Yeah.
So that's super low. So that's out. 10 Kelvin, super duper low. So that's out as well. C and D have the same temperature. And now we can just compare the pressures. I mean, one is 50 pascals, the other is 50 kilopascals. And you want something that has, a lower pressure, right? You want high temperature and low pressures.
Yeah.
So,
So C is way better.
mm-hmm.
Mhm. Yep. I see now. Just don't think I was thinking properly when I was doing the question.
Yeah, that's, they messed with you in terms of the units. Because if this was 285 Celsius, it would be the highest temperature, right?
Mm-hmm.
And if everything was in atmospheres, that's the lowest pressure. So, you have the right idea. It just, the fact that they're not all in the same units.
Yep.
Mm-hmm.
And Pascal is bigger. Wait, 1 ATM is like 1,000 pascals or something. 10,000 pascals, roughly 13,000.
Uh oh,
What?
101.3 like kilopascals, I think, is equal to 1 ATM, something like that.
Right. 101 point. Okay, kilopascal. Right. Okay.
Mm-hmm.
Okay. Next question is a organic chemistry question.
Okay, so all right. Addition of aluminum hydride to sphingosine. So, sphingolipids and stuff like that, they're like, in our brains, there's like it's yeah, they're yeah. Okay. So anyway, um a lot of like brain disorders in Ashkenazi Jewish populations involve sphingolipid issues. So you see, like, they talk about Tay Sachs later, like in that passage. So they're just think of them as like a type
Oh.
of like lipid that you know is basically there. It's going to be in your brain.
Mm-hmm.
Okay. So, all right. So they're saying addition of aluminum hydride. What's hydride?
Like hydrogen, like H, basically.
H what though?
Depends on the Well, aluminum hydride, I'm thinking like AlH3. That's what I'm thinking.
So I mean, let me ask you this: like NADH, right?
Yeah.
Like this over here is a hydrogen with 2 electrons, making it negatively charged.
Right. Hydride. So hydride is hydride negatively charged?
Yeah.
Yes.
And hydrogen with 1 electron is normal.
Mm-hmm.
And hydrogen without any electrons is just is positively charged. It's just a proton.
Mm-hmm.
What about hydrogen with um, you know, a neutron?
Is that a deuterium or
Yep.
something?
What about with like 2 of them?
Uh, like
Tritium?
tritium or
Mm-hmm. Good.
okay, sounds
Yeah.
good.
Tritium is pretty cool. Like they use it on like well, I mean for a lot of things, but like some like firearms, like pistols and stuff, they have like tritium sights because they glow in the dark and they're not they don't need like, electricity or anything like that. So they make like a nice glow.
Wow, that's cool.
Mhm.
Wow. All right.
So anyway, hydride is negatively charged, okay?
Mm-hmm.
So that's why you see like whenever like NAD plus turns into like gets reduced, right?
Mm-hmm.
It's NADH plus H plus
Yeah.
in like a a metabolic pathway kind of thing.
Yeah.
Okay.
Wait, why does it get a H plus?
No, oh, because it gets reduced.
Yeah.
So uh, we have to do like it has to be like same uh like conservation of charge and stuff.
Oh yeah. Yeah. Okay.
Yeah. So since it's gaining an electron, since it reduce means gains electron, so it gains an electron in the form of hydride. Um, but yeah, it gives off like an H plus because this is positively charged, and this has to be like the total of that has to be positively charged.
Okay. I see.
Yeah. So okay, addition of aluminum hydride to sphingosine would most likely result in which of the following products? All right, so there's a lot going on here. So let's see what they say about what happens when you add stuff to this stuff. Um. Okay, it. So this might be some of those like one of those reagents to know,
Yep.
like
Yeah.
aluminum.
Yeah. Like I know that
Oh,
it's
I should
a
also say that when this hydride is like introduced, this doesn't stick around with the NADH. That proton is just given off. So
mm,
so yeah. So yeah, hydrides. You know. So okay, hydrides are basically hydrogen donors that are used as reducing agents.
mm-hmm.
Um, so if something's a reducing agent, what happens to it?
It gets
All right,
oxidized.
perfect. Okay, so all right, if you see aluminum hydride, just think of it as a reducing agent. I think I had like oh yeah, in one of my notebooks I have like kind of like um like a list of like some reagents to you know. Um,
Mm-hmm.
like KMNO4 stuff like that.
Yeah. NABH4. Yeah, I also have a list too.
Yeah. Okay, got it. So like oxidizing agents, KMNO4, you know, NAD plus, FAD, you know, stuff like
Mm-hmm.
that. Reducing
Mm-hmm.
agents, things like NADH, um, like lithium, aluminum, like H4, and
Mm-hmm.
then sodium, BH4, stuff like that.
Mm-hmm.
So, yeah.
For sure.
Okay, so yeah, so that's something you're for orgo to like to know, I suppose.
Definitely. So I guess when I saw this question, I was like, okay, this is gonna be a reducing agent. I was like, okay, great. And then I looked at the sphingosine. I was like, it's already reduced. So I was like, wait, what do I do?
Oh, okay. So all right. So this okay. So there's something that um. Oh man, I keep saying that I'm gonna share these like things with your notebook, but I still haven't done it. So my bad.
It's
Um,
a,
but like for instance, um, so here. So this over here, you gotta know. Okay? So like, you
yes.
know, so if we go left to right via oxidation, right?
Mhm.
Which you know, catabolism is oxidation. So let's say you start off with like an alkane, like a single bond, right? And you
Mhm.
oxidize that, it turns into a double bond,
Mhm.
and you oxidize that again, and it'll turn into an alcohol.
Right.
Now, it can be a tertiary alcohol, a secondary alcohol, or a primary alcohol. If it's a tertiary alcohol, it stops right there. You can't oxidize it any further.
Mhm.
Um, if it's a secondary alcohol, it will be oxidized into a ketone.
Mhm.
But after that point, cannot be oxidized further. If it's a primary alcohol, it'll be oxidized into an aldehyde. And if you oxidize it again, it'll turn into a carboxylic acid.
Mhm.
And, you know, so I kind of use like an example of like PCC. I forgot what that
Yeah.
stood for.
Like
But
iridium
yeah, probably something. Yeah. Some,
bromate or something.
yeah, something like that. So that's not that strong of an oxidizing agent. So it'll like just turn it into the aldehyde. But if you use a strong one like KMNO4 or CRO3, it can go all the way to the carboxylic acid.
Mm.
And then, you know, at the carbox, like if you oxidize it one last time, it'll turn into just CO2. All right. And, you know, that can be done via, you know, these things, right?
Mhm.
Now, you know, the opposite direction is reduction, and that's done via this stuff. So this is very, very, very important to look at or to know. So I would have that memorized as well. Like
Mhm.
I say, I don't like memorizing things, but I just think it's better. I just have a disagreement on what to memorize. Like I think it's better to memorize like these general rules, conceptual stuff, instead of just
Yeah.
like every you know metabolic pathway and stuff like that.
Yeah. No, I
So
definitely like think about the reasons behind these things. Like for example, NH3 because it has H3, then it's able to donate protons, so then it gets reduced.
mm, well, you mean donate
No, like donating. So donates protons. So then the thing
Donate
that gets the
protons?
gets reduced.
Does but protons?
Yeah, like H, because uh, getting a proton is also reduction.
All right, but are you sure that we're talking about protons?
Well, H plus or whatever.
So they're electrons. Remember, you can't do things with protons. It's all the way inside of the nucleus.
Right.
So
Yes.
it'll donate electrons, right?
Mm. Yes. But isn't it like there's another way to think about reduction is like if something gets a hydrogen?
Um, so you can think about it as something that, like, all right, let me put it this way. So it ultimately comes down to the electrons. Generally speaking, hydrogens can play a role, but the hydrogen is going to be like some type of like hydride or something else. But what happens with ammonia is, so ammonia, right? So ammonia has a lone pair,
Mm-hmm.
right? So it's going to um, it's going to reduce things, right? Like, like Gur, right?
Yeah.
So gain of electrons reduced. So if it reduces stuff, it's going to donate, you know, that,
Mm-hmm.
right?
Mm-hmm.
So, um, so I guess you're thinking about ammonium, maybe.
No, like for example, like just NAD plus, if it turns into NADH, then it's reduced. Like,
Yeah, but it's, so remember, that's a hydride right there. So it's not really gaining a proton; it's gaining an electron.
right. Yeah,
Yeah.
that's right.
So like
Yes.
here's like, fundamental rule here, like no protons. Whoops. No protons you know like like wandering. um all right.
Right. But
Like
yeah.
even when they write H plus, like for acid, it's really H3O plus hydronium.
Right.
Yeah.
Yeah.
But the protons are in the nucleus. It's very, very pretty much like, yeah, you're going to have to puncture the nucleus and get past the strong force in order for, in order to do anything with protons. Okay.
Mm-hmm. Right. Yes. Yes.
um yeah, so okay, but yes, that hydride part is important because, yeah, it always comes down to electrons. So this guy gains electrons. It seems like it's gaining a proton, but that's just a hydride.
Mm-hmm.
All right.
Yep.
Okay, so let's see. So I see a sphingosine, right?
Right.
And I see alcohol groups.
Mm-hmm.
And if you reduce an alcohol, so first of all, I have a secondary alcohol and a
Mm-hmm.
primary alcohol, right? The
Mm-hmm.
secondary would turn into what?
I'm thinking, well, gets reduced. I'm thinking it will turn into a double bond.
Yeah, good. So, yep, that yeah, that's pretty much what happens. Um, so all right, so let's see this stuff.
So that was my reasoning because I was like, okay, if it's gonna get further reduced, then one of these OHs are gonna turn into double bonds, which is why I chose an answer that just has a like ino or whatever, like without the dial because dial means there's two. So I was like, oh, that doesn't make sense.
Mm-hmm.
But then it seems like I don't know, like the
Oh,
I don't
oh, we forgot about that double bond. That gets reduced to a single bond, right?
yeah. Oh yeah, yeah, yes. Oh, okay, okay. Then I see.
And I all right. So I didn't show you like this part. So you see how all of these are greater than
Okay,
symbols?
I see.
So if you threw in like a reducing agent or something, or oxidizing agent as well, it's going to work on this stuff before it works on that stuff.
Yes, yes. I did not see that.
Mm-hmm.
Right. So then because okay, okay. So then the answer is D because aluminum hydride will work on the double bond.
Uh, yeah. So let's see. Oh wait,
Everything else will remain the same. It seems like.
I don't know why that just disappeared. Okay, let's see. Okay, so yeah, so the double bond should turn into a single bond. Um,
And then
and I think they're saying like just addition of aluminum hydride. I don't know if they're saying like you're adding it like over and over again. Um, but that could be a possibility. So let's see. Well, hold on. So then we get a die. Okay, so let's see. So basically, this thing turns into a single bond. So, and also it always helps to see like what's different. Everything
yeah,
else has an ene to it.
for sure. And you just cross them
Um,
out.
C doesn't even have the amino part of it.
Right. Exactly.
Um, so, so okay, so this thing turns into a single bond. Um, and amino octadecan 1,3 diol. So, you know, um, so all right, this is like the one position, two position, three position, right?
Mhm.
And then four position. Sorry. Yeah, four position is where that double bond starts.
Mhm.
So that four double bond is going to be gone.
Yeah.
Um,
Yeah.
now, so okay, it seems like okay, one, two, three, yeah, okay. The alcohol groups stick around.
Yeah. Exactly.
So I think it. So they're saying if you uh, if you just add it, what will happen? It doesn't say what will happen if you keep adding it.
Yeah.
Because if you keep adding it, then
But
yeah.
I think even if you keep adding it, the double bond should still be the one that gets reduced first.
So you add, let's say you add one aluminum hydride, right? Double bond is gone. Add another, it's going to take away, it's going to take an OH group and turn it into a double bond.
Right.
Add the third one, it's going to take that double bond, turn it into a single bond. Add a fourth one, it's going to take another OH group, turn it into a single bond. Oh no, turn it into a double bond.
Mhm.
Um, and then you add a fifth one, it'll turn it into a single bond.
Yeah.
So that's that's why it's like whatever. Yeah. So that's what you're going to get. It would have been a harder question if they had something identical to D, but with a different It seems like
Like
all of them have two S and three R,
yeah,
because
exactly.
that stuff can be kind of annoying.
hmm Yeah,
Do
for
you know
sure.
like how to do that kind of stuff?
Yeah, I think so.
Um.
I sure hope I do know how to do that.
Okay.
So you just name. So find your chiral center, and then you name from like 1 to 3, and then like which way it turns, and then like you give the
Yeah.
result.
So you want it to be like, why did I
The
open
highest
PowerPoint?
one is like the highest like atomic number that's closest to the chiral center will get named 1, and then you just like rank. And then, for example, the OH in the third position, because it's a dash, that means it's like behind it. So then you reverse the trend, basically.
Yeah. So I would write like it in such a way that like the lowest priority group, like the hydrogen, is out is into the
Mm.
page,
Mhm.
right? So are that ammonia, that amine group is towards us out of the page. So okay, whoa, that's bigger than I thought, but whoops. All right, I'll just do it on the whiteboard. So whiteboard. Okay, so basically, let's say OH, NH3, OH, and then blah 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 blah. Oh yeah, there, right?
Mhm.
So this over here is the hydrogen, lowest priority. So in order of priority, this is 1, this is 4, right?
Mhm.
So what's going to be next?
I
Is it
think
going to
the
be this
OH in the
guy
third position is
or this
2.
guy?
I think the OH in the third position is 2.
Um, yes, because it's attached to a carbon that is attached to two different things. So yeah, that'll be 2, this will be 3. And
And then
so it'll go in
the
this
it's counterclockwise.
counterclockwise position. Yeah, what's up? Oh, wait, were you
Oh
saying?
no, I was saying that it's S.
Yeah. And
Yeah.
then, for this one, the H is like here. So this is 1, that's 4. This over here should be 2. This over here is 3 going clockwise. And that'll be R.
Mhm. Yeah.
Okay.
Mhm. Makes sense.
You know why it's called S, by the way?
It's I don't remember.
So, um, do you know the word sinister?
Sinister, like in English.
Yeah,
Sinister, like bad.
bad, right? So, it comes from Latin, like sinistral, because they always associated the left hand or the left side as being bad. So, sinistral means left, like left handed,
Mm.
or, left something. Um, you know, but, yep.
Yeah. There's also like origins for like the D and L thing
Oh,
too,
yeah,
right?
dextro
Yeah.
and levo.
Something yeah, something like that.
Yeah, so that's yeah, that's the you can do it like that. Yeah, you can do it like that also. That happens like it more in the context of how it rotates like plane polarized light, like dextro rotary levo. Yeah. Okay, good. All right, it's
Okay.
good that you understand that stuff.
Yeah.
Oh,
Thank
let me see what they're saying. All of the electronegative atoms, oxygen and nitrogen, have their electron affinity partially offset by sigma bonds to other elements. Okay. All right, and then they say, and they give good explanations here. So, you know, gain of an electron, decreased oxidation state, formation of a CH bond, alkene to an alkane, loss of a CO or CN. Yeah, basically the stuff that that we talked about. And then then we see the spectrum of like oh yeah, okay, PCC, and then like the chromium or whatever thing. Okay.
Yeah. No, this question makes sense though.
Yeah. By the way, when you see lithium, aluminum, hydra like H4, NaBH4, the lithium and the Na part aren't really that important.
And they. Oh, right.
Yeah. I can like get into the reason why. But I don't know. Why don't you tell me why is the thing with aluminum H4 a stronger reducing agent than boron H4?
Oh, I feel like I should know this. Okay, so boron versus aluminum. Because let's look at the periodic table. Because aluminum is aluminum is a bigger atom. It has to do with one of those trends, I think.
Okay. So
The
like
table.
yeah. One of the most important trends is because you can kind of like deduce the rest from it is like electronegativity,
Mm-hmm.
which means that it wants electrons.
But boron wants electrons more, I think, than aluminum,
Yep.
right?
Yeah. So
So,
if it's so a reducing agent causes something to be reduced, like gives its electrons away, and yeah.
So because boron is more electronegative.
Oh wait, sorry. A reducing agent. Oh yeah. Sorry, gives its electrons away.
Yeah.
And
So
boron doesn't want to give them away as much.
it wants to have it for itself. So
Yeah.
that's what it's okay. Makes sense.
But it's also good to think of atomic radii. Like if you had, like if you're comparing like these like acids.
Mm-hmm.
Like I remember seeing an episode of Breaking Bad, and they said like this is the strongest acid, like that. First of all, like base, like all right, I'm not gonna even get into it, but like most like acid attacks are actually bases, and like acids are corrosive, which means that they can damage inorganic material. But bases are caustic, which means that they cause really bad damage to organic material.
Mm-hmm.
And the reason behind that, without getting too much into it, is because if you see a comparison between acid catalyzed hydrolysis of like DNA or a fat or anything like that, it just does it once. But with a base, it just creates another OH minus. So it's like a chain it's an irreversible process. If you spilled acid on yourself, like it'll do some damage, but predominantly just because it's an exothermic reaction, so you might get some burns.
Hmm.
However, if you spill like a base on you, it's going to eat through everything until you neutralize it. So,
Totally.
do you know
That,
like what Drano is?
yeah, for your drain, for your.
Yeah, yeah. So that's what, if there's hair stuck in your drain, like, like organic material, it like, it eats through all of that.
Yeah,
And
totally.
that's what you don't want, to spill on yourself.
Yeah, totally. Like my mom spilled like this like alcohol solution in her eye.
Mhm.
It's really bad. Like
Yeah.
recently.
That'll
So
like, that'll like hurt first of all, but at most it'll just remove the epithelial layer of your eye. Like I worked for like a laser eye surgeon when I was like 18 and one of the most advanced like LASIK procedures is like LASIK, not with an I but with an E. Most people get the one with an I, which means that they cut a flap in your cornea, they flip it open, and then they, shoot lasers at it to, shape the topography, and then they close the flap. And every single complication that uh, came from laser eye surgery was flap related. But LASIK with an E, it involves putting like an alcohol solution in your eye, which just takes out the epithelial layer, and then you shoot the laser at it, adjust the topography, and no flap. It's not invasive.
mm,
Yeah. So
that's-
oh yeah. So basically for these, like what like tell me about like the strength of these acids.
strongest is iodine, and then
Okay.
you go
So yeah, tell me why.
because iodine is a really big atom,
Yep.
or the periphery of, so the valence, wait, no, yeah, valence electrons are like, it's easier to just like, wait,
Mhm.
no, give off.
Yeah, yeah. Yeah, basically. Like
Fluorine is like electronegative. It's like it's very, it has like high Zen effect or something, and it just wants electrons, so it's hard to like rip it off.
yep. Yep. Good. Good job. Okay. So, yep. That is right.
Great. Um,
Um okay, let's see. The next one. All right. In a follow-up experiment, researchers um sorry, I was just looking at this cuz it's pretty cool. Um like the passage. So okay. Okay. A new system including all chambers with the same initial volume as the experiment and the pressure. Okay, so I'm going to have to like look at this. So let's see. Noble gases neuroprotective effects. Perinatal hypo. Okay. It's funny, like when I was like 6 months old, I had like like hypoxia like to my brain for like a period of
really?
time. Yeah, I should be like it's a miracle that like I survived and like didn't like lose my like cognitive function.
Maybe that's why you did so well on the exam.
It's crazy, isn't it? um, but yeah, like that's basically what. Yeah. So okay, let's see. Yeah, and one of the things like the first things I did when I worked with the laser eye surgeon was on a patent for oxygenated eye drops, which supply oxygen to your eyes. So for hypoxia, but okay. So let's see. Okay, argon, helium, and xenon are all right. Okay, so right. Okay, ligation. Okay, chamber with the following gases: a noble gas to oxygen ratio of 7 to 3. Total volume was 3.5 liters at basically one ATM, um, which kind of can make you figure some stuff out, like the amount of moles. I'm just like thinking, actively,
For sure.
like the 22.4, I think, or
Oh,
whatever, right?
22.
That's if it's ideal, of course. Okay, and 23 degrees Celsius. So they're giving me volume, they're giving me pressure, they're giving me temperature. So I bet we're gonna use some ideal gas law stuff.
Mm-hmm.
And
I,
no reason to know Boyle's law or Charles' law or any of that. Just know ideal gas law because it
yeah.
just has them all
For
and
sure.
things cancel. So all right,
Yeah.
now soda.
Question,
Yeah.
just like I knew you're supposed to use the ideal gas law, but I didn't use it correctly. So
Okay, let's see. So soda, lime, and silica gel were added to eliminate H2O and CO2. So silica gel you'll find in like a lot of stuff, like those like little beads. They act
yeah,
as a desiccant.
for sure.
Um, okay.
Oh,
Untreated. Okay, so okay, the control. Wait, untreated. Okay, control. What's the control then?
um,
Oh wait, so I see. So the control is just nitrogen gas.
I forgot what the control is.
Okay, so all right. So the naive group um just stays in something with um nitrogen. The control. Oh no, sorry. Noble gas. Wait, what? Okay, I'm gonna forget about naive for a second. Oh wait, untreated pups. Untreated. I guess that means that they didn't have the that coronary artery ligation.
The untreated.
So basically, what they did was they 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 uh they basically um like tightened a coronary artery, right?
Mm-hmm.
And that's the control where they're just in a nitrogen chamber. The naive are just the people who didn't have that coronary artery ligation.
Mm-hmm.
So that's like a control.
Right, right,
Okay.
right.
Um. All right, and then we can compare the wait. What is this number of cells? Okay.
Yeah.
So cell
But
survival. Okay, so number of cells is cell survival. So nitrogen only seems to be the lowest. Argon uh, seems to be the highest. Helium and xenon seem to be pretty similar.
yeah. Well, this question is like I think kind of discrete. I don't think it's related.
Oh yeah, yeah,
So
yeah, yeah. I was just kind of interested. All right, let's see. So they're saying that pressure is 2 atm, allowed to expand. So volume 1, or sorry, pressure 1. Wait. Okay. All right. So basically, pressure 1 is 2 atm, I suppose.
mm-hmm.
Pressure 2, I think it. All right, let me just see. So, blah blah blah. volume. Okay, volume doubles, right? 3.5 to 7, right?
Mm-hmm.
And the pressure also doubles because 760 millimeters of mercury is 1 atm,
Mm-hmm.
and the pressure doubles as well.
Yeah.
Um. Oh wait. Okay. Hold on. Hold on. So they're talking about different stuff here. So they're first saying that um same initial volume as the, so this is a new experiment. So same initial volume as in the experiment. So V1 is equal to 3.5 liters. Pressure
Mm-hmm.
1 is in the new experiment, 2 atm.
Mm-hmm.
Um, the new volume is 7 liters. The new
Mm-hmm.
pressure is also, it's the same as
Right.
before. So we're not going to, use the pressure part. Okay. Now, by what factor would the temperature inside the new chamber change? Right? So,
Yeah.
this is so, ideal gas, blah blah blah. So like whatever, PV is equal to nRT, right?
Mm-hmm.
So I'm just going to, since I'm going to deal with two versions of that, I'll just write, you know, like whatever, PV over nRT is equal to PV over nRT.
Mm-hmm.
So tell me what we can cancel.
R and
And what?
and mole.
Yep. Now, what else can we cancel?
Pressure,
Yep.
because it's kept constant.
Yep.
Yeah.
Okay. So in order for this to be equal, right, the volume doubles, like volume 2 over here. So, yeah. So the volume, doubles. So how can we, rectify this in order for these to be equal?
Mm-hmm. The temperature has to double as well.
Correct.
Oh, okay. I was thinking, oh my God. I was thinking about it like, okay, if the volume increases, then the temperature has to decrease. And that's not right. So,
Volume increase, temperature has to increase. Um what well, I mean, I guess like in general, like temperature, if temperature increases and you don't change anything else, like it should cause the volume to expand, right?
right.
Um I think
Right.
I see what you kind of were doing.
Yeah, but it's
Like
like,
if you cross multiplied this, V1 T2 is equal to T1 V2. So like if this guy gets doubled, oh yeah, no.
no, it's,
Wait,
yeah.
temperature in the new, yeah, yeah. So, yeah, I could see what you're doing. It just on the wrong temperature, I guess. Like if T1 was 1/2, then, they'd cancel,
Yeah.
right? If
Yeah. Yeah.
T1 was 1/2, then they'd cancel, yeah.
Right.
But since T2 is all the way there and V2 is here, if this guy gets doubled, this has to be doubled. You know, like on an equation, whatever you do to one side, you have to do to the other.
Yeah, for sure.
Okay.
Okay. All right.
All
This
right.
question.
All right. These are like my favorite. The photon questions.
Yeah, I like them too.
Mm-hmm.
But
Yeah.
they're
Yeah. So, you know, let me show you. Yeah. Okay. I have like shortcuts for this stuff as well. Okay. So, radiation oncologists use machines called. Oh, nice. Gamma knives. Those are really cool. Lead vests are used to protect non-cancerous areas and medical personnel from radiation exposure. Typical gamma knife uses a photon beam with a frequency of, so the frequency is super high because it's a gamma rays.
Mhm.
Suppose a stray photon hits a lead atom and ejects an electron, um, and a lower frequency photon of that much energy, which is still going to be a gamma ray, right? What is a
Mhm.
maximum kinetic? Okay, so there's something. Whoops. Okay, so there's something to know about. Um, okay, kinetic energy of a photon is equal to. Um, no, sorry. Kinetic energy of an electron is equal to um, the energy of the photon minus this thing called the work function.
Oh, what? I've never heard of that before.
Yeah, so the work function is essentially just um, it's basically the energy required to make the electron no longer bound to the atom.
Mm-hmm. Oh, wow. Okay.
Yeah, so like, let's say that we have, some, photon that causes an electron to go to, its excited state like this.
Mm-hmm.
And then, so it's still bound, it's just, further away. Okay, and now let's say that the energy of the photon is enough to make it not bound. So let's say that this electron then is no longer bound. So that's what happens when the energy of the photon is equal to its work function, which is basically like kind of like ionization energy.
Mm-hmm.
So okay, that means that it's no longer bound, but the electron is just sticking around because it doesn't have enough energy to move.
Mm-hmm.
Now, if that photon has the energy of the photon, if that's greater than the work function, then that excess energy is going to cause that electron to be, ejected with
Right.
a velocity.
Right.
Okay, so yeah, this is a good one to remember because it comes up a lot.
Yeah. Oh,
So
I've just never seen that before. Wow, it's so weird. How did I
mhm.
miss that?
Yeah, so basically, ejects an electron, so that's what's happening, and then kinetic energy of the ejected electron. So that's that part right there. So
Okay, got it.
basically, oh, and then they say work function right there.
Right.
So that would be this guy over here. And then energy of the photon. So what's the formula for that?
Uh, Planck constant times frequency.
Yep. Which can also be.
HC over lambda.
All right, good. And since HC comes up a lot,
Mm-hmm.
I think it's also useful to remember this. So, because Planck's constant times the speed of light is annoying to do. So, check this out. So, the 6.6, blah, 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 right?
Mm-hmm.
So, that basically comes down to like 6 2/3,
Mm-hmm.
which is basically 18 plus 2, 20 over 3, right?
Oh, yeah.
So let's say 20 over 3 times 10 to the negative 34 times what's speed of light?
3 times 10 to the 8.
So these threes cancel.
Perfect.
So you basically get 20e um, negative 26.
Yeah.
So that is very useful to remember as HC.
So that will be 2 times 10 to the 25th?
Oh,
25?
oh, yeah, if you wanted to do that, like with perfect whatever scientific notation, but, only do it if you have to. Because generally speaking, right, you're going to have some number underneath or something, and it's easier for it to go to 20, but, you know. So, yeah, that's just very useful to remember. Because these threes just cancel.
Mm-hmm.
It's
Yeah.
like, there's so many things like that I notice that a lot of people don't notice. Like, if 4/3 pi are squared, or wait, cubed?
Yeah. It's the volume of the sphere or something.
Yeah, but pi and 3 are essentially the same, so it's really just 4 times that.
Yeah.
So, for a cone, it's like, similar kind of thing, right?
Mm-hmm.
But those just cancel, yeah. Anyway,
No, it's
and
good.
3.14 is just 3 and 1/7. But anyway, so let's see. So, okay. Okay, so I guess the most stuff we're going to do here is deal with okay, I guess we're gonna deal with a couple of things here, but electron volts is one of them, um, which is also something that I have memorized, which I think is useful. I am pretty sure it's like 2.5 or something. Wait. So, okay, I'm gonna share this thing with you in the notebook as well. Basically, wait, not that. It's like math. Like this stuff is like super useful to memorize right here.
Mm-hmm.
Oh yeah, here H in electron volts. Um, you know, it's this stuff.
Oh, okay.
Just yeah. And you see how I also logs are also going to come up, so I also incorporated that into the sine cosine stuff.
Oh, okay. No, that is very useful.
Yeah, and if you know these logs, you can find any log.
Wow. Okay. That's cool.
Yeah. So okay, so basically, so okay, Planck's constant is 4.1 e negative 15 electron volts times seconds. Let me go back to this. So 1 electron volt is equal to that many joules, but you know, like you would know how to do it also, like if you did the math or whatever.
So I guess yeah. So I understand how to calculate it, but how does sorry my thing is
Mm-hmm.
um how does work function in EV will oh it's cause okay I see you need to convert it to joules. Okay, that's why. Okay, got it.
Oh yeah, yeah. So okay. Um I did the electron volt thing too fast. Okay, so basically here, I'll do that here. So basically, let's just do. Here, go to that. Okay. So let's find, each of these, right?
Mm-hmm.
So electron energy of a photon is HF, which is just, basically like I'll do the 20/3 thing again because I like that. E negative 34 times 1.6 is 1 2/3, which is just 5. Wait. It's what am I talking about? 1 2/3 is 5/3, right?
One.
I'm going crazy. 5/3 goes into it
Yeah.
1
Yes.
2/3. Okay, so 5/3 E 19. Okay.
Mm-hmm.
So okay, then I get 100/3 E. So negative 34 plus, I'll do 20 because it's easier than 19, and then I'll subtract. So basically negative, or rather positive 14, and then that's too much, so positive 15.
Mm-hmm.
So am I going in the wrong direction? What am I talking about here? Wait, I'm looking at some frequency of 1.6 times 10 to the 19 hertz. That is okay. They're saying 10 to the 16 hertz. 10 to the 16 hertz. Oh, they're subtracting it. Aha, ha. I see. A stray photon has that frequency right there.
Right, because you need to, because
The
it's like reflecting, right?
1.599 part.
Right.
So, okay. So basically subtract the 2 so you get rid of that. So it's just straight up,
Yeah.
19.
Yeah, for sure.
So basically 6.6 E let's see, negative 34. I'll do plus 10 is negative 24 plus 5, or I'll do plus 4 negative 20 plus 2 negative 18. There we go.
Mm-hmm. Yeah.
Okay, so that is the energy of the photon in joules. All right.
Mm-hmm.
So, okay, and then basically the work function is in electron volts. We got to change that into joules.
Yeah.
So, let's see, 4.14 electron volts. Oh, wait, you can't even see what I'm writing. So,
I feel like AMC never does like calculations with this many steps.
oh yeah, that's why it's great practice, because that means that you can take whatever they throw at you on the actual test when they do want you to do crazy stuff.
That's true.
Yeah, I remember spending so much time on one problem about radioactive decay, and it was about radon, and I used the period. I used a radium on the periodic table. Anyway, so okay, one electron volt is 1.6. I'll use 5/3 E negative 19. The math is annoying. Whatever. That's like roughly like 20/3 E neg 19.
Mm-hmm.
20/3 is like 6.6. Whatever. Like it's gonna be a little. Whatever. So yeah, times 10 to the negative 19. So that is a work function. So we just subtract the two.
Mm-hmm.
So that's just 6.6. It's the same. By the way, this thing in the beginning of scientific notation is called the mantissa, I believe. Anyway, so the mantissa is basically the same, and this guy is just larger by a factor of like 1. So it'll basically just be like 66 or negative 18 minus negative. Oh, wait. Oh, okay. No, sorry. Negative 18 minus negative 19 is negative 18 plus 19, which is 19 minus 18, which is just 1. So it'll just be 6.6 E1? What am I doing here? 6 point minus. Oh, I'm not multiplying them. Sorry. I'm subtracting them. So I'm subtracting them. Sorry. So basically, it's like basically 66 minus 6, if that makes sense.
Mm-hmm. Yeah, that makes sense.
Because, because this one is just larger by a factor of 10. But yeah, so this could be 66, this can be whatever, 6 or something. So yeah, you'd end up with just or 60. But anyway, you would get the yeah, so if you just use that work function thing, you should be getting that right there.
Mm-hmm. Yeah.
So yeah, so basically, yeah, so we're just so yeah, the work function thing, this over here is what you need to know for this.
Mm-hmm. Okay, sounds good.
All right, the next one is electrolytic cell.
Yeah, this one is, I don't know, confusing.
Yeah, so okay, so let's see. Electrons flow into the electrolytic solution from. So okay, people say just to know that, in a voltaic slash galvanic slash, basically a battery, right? The cathode is positively charged and the anode is negatively charged.
Mm-hmm.
And they say in electrolytic cell the opposite is true.
Yeah.
But it helps a lot more to think about it like this, like a here, let's see. Whoops. Oh wait, it's on the same thing. So here, so okay, check this out. This is the best. So I'm gonna share this with you. I know I keep saying that, but this is the best way of looking at it. Okay, so this is a regular galvanic cell, right?
Mm-hmm.
Which is a battery, basically, right?
Mm-hmm.
The anode, right? It has a negative charge. Okay, and that means it's sending electrons to the thing that has a positive charge.
Mm-hmm.
So as that is running, right,
Mm-hmm.
the negatively charged anode accumulates positive charge through the loss, of electrons. And the cathode accumulates negative charge as it gains electrons. So this reaches a point where, essentially, the battery is dead. There's no more of a current that is going between the two.
Mm-hmm.
So this is where I say eventually all of the electrons will reach the cathode all of the cations will reach the anode. This is equilibrium. In other words, a dead battery. Um, and a battery, or an electrochemical cell, or a galvanic cell, or a voltaic cell, all the same thing.
Mm-hmm.
It turns chemical energy into electrical energy. So what do you do when you have a dead battery? You charge it, right?
Mm-hmm.
So you plug it into an outlet, and you're doing the opposite now. You're using electrical energy to recreate that, that chemical. You're recreating the chemical energy aspect of it. So
Yep.
that, yeah,
No, I understand that part.
yes. So that's why the things are negative and stuff like that. So okay, electrons flow electrolytic cell into the electrolytic solution from.
I thought electrons always flowed from the anode to cathode, so that's why I chose A. But
Yeah, except when it's dead, right? So a regular battery, it'll go like that until it's equilibrium,
mm-hmm.
and then you use electrical energy to force that change in, concentration and stuff.
So is the passage charging the battery?
Yes, like
Wait.
electrolytic cell, examples of it are, um, charging a battery. You could also electroplate. And then this, we kind of had I remember we had a question about this before, where in some process of making ammonia, they use electrolysis.
Oh, okay.
Yeah. So I wrote say you're in a submarine underwater, how do you breathe oxygen? So they use electrolysis to make oxygen from H2O.
Hmm. Hmm.
Yeah. So these, I mean, yeah, you could do these things with an electrolytic cell, but yes, charging a battery, a dead battery, is is that as well.
Okay, that makes sense.
Yeah. I have another thing here where I talk about it, but yeah, I think yeah, here's a real life example, like a lithium ion battery in your phone.
Mm-hmm.
So etc. So yeah, for this one, they're just saying, um, so yeah, an ox and
Mm-hmm.
red cat are always true. You just have to think about when the thing is happening, right? So if the anode is where oxidation happens, it means that it's losing electrons
Mm-hmm.
until it's lost them all, which would make it a positive charge. That's when it goes from a voltaic cell to an electrolytic cell. Okay?
Mm-hmm. Yeah, makes sense. I
Good,
I guess
good.
just I
Mm-hmm.
guess I just didn't do this question based on what they describe in the passage.
Oh yeah,
I just
no, you don't even need to do that. I
mm-hmm.
didn't even look at the passage. You just that's just how electrolytic cells always behave.
Okay.
So
Okay.
yeah.
But I just thought electron always flows from anode to cathode.
Oh wait, what's up?
I just always thought that electron flows from anode to cathode for both electrolytic and galvanic cells.
It'll happen for a galvanic cell until it becomes, until it loses all of its electrons and it becomes positive and the other guy gains it all and becomes negative, then it'll be, uh, you know, then you would add an external source to force that to happen again. So that's
Mm.
why it says positively charged anode, right? That would be the case if it was for, whatever, galvanic, but the thing that is going to happen is that the cathode, aka reduction, aka gains electrons, like, it will be basically, yeah, from that, I guess. So, all right, let me look at the explanation. So, cathode is negatively charged, okay? And yeah, opposite is true. Anode and cathode are defined not by their charges, but what happens, like oxidation or reduction. So, if electrons flow from something, right, that something loses the electrons, which means that something gets
something loses an electron, that means it's oxidized.
Mm-hmm.
Right.
Yeah, so it should be from the passage. All right, you know what? All right, I'm gonna look at the freaking passage. Okay. So let's see. What is the? Okay, so they're saying electrolytic cell, redox. Okay. Reduction happens in the negatively charged cathode. Okay. All right. So what are they saying here? Electrolytic cell into the electrolytic solution. Okay, I see. The solution is what they're asking about. They're not asking about what is traveling across the current carrying wire. So it's not going to be that. So they're just asking what is basically. So how are the electrons essentially getting into the solution?
From the battery.
Well, the battery is the thing that makes the electrolytic cell like work, because the battery, like, to like recharge it essentially. But so if you take a closer look at what they're kind of showing you there, so okay, the cathode, right, is where reduction happens, which means that it gains electrons. So if it's gaining electrons, it's not going to, because there's always like a solution of anions and cations.
Mm-hmm.
Like that's why, in a voltaic cell or whatever, you have two of these and then the salt bridge. That just, in order to complete the circuit.
Mm-hmm. Yeah, for sure. Okay.
Yeah, so basically the answer to this is going to be the negatively charged cathode, because because as it gains electrons, it's going to basically it's not going to take in the anions in the solution.
Mm-hmm.
And they're asking about electron flow into the electrolytic solution. Where does that come from?
Right. Okay. So the solution is also acting as a anode or cathode?
The solution is acting as, like, as so this is like, without a salt bridge.
Mm-hmm.
But that salt bridge, just right, the solution acts as something that completes the circuit.
Oh, okay. Right.
Because electrons are going from the anode, or rather, the battery is making it happen. But anyway, the wire is how the like the solid metal, like, electrodes are getting or losing electrons. The solution, however, is what completes the circuit, because they're not, there's no like complete circuit here without that electrolytic, without the that solution.
Mm-hmm. Yeah. Okay, makes sense.
Is there any question about uh this like overall topic?
You mean electrochemistry?
Mm-hmm.
Not really. I think I have a pretty good grasp of like electrochemistry, so not really.
Uh-huh.
Yeah. I say I'm fairly comfortable with electrochemistry.
Yeah. So like if you looked at this over here, which is like a regular, galvanic cell.
Mhm.
Let's say we got rid of that salt bridge.
Mhm.
You're not going to have you're not going to have like this work
Mhm,
like
for sure.
because electrons are going leaving this guy to go to this guy, which means that this guy doesn't need you know um uh like the anions basically, because the solution is going to be, so okay, this is like a zinc solid electrode, this is a copper solid electrode. This solution is zinc and sulfate.
Mhm.
This solution is copper and sulfate as well. So there's going to be like, so okay, if zinc is losing electrons, it's going to produce a zinc cation, right?
Mhm.
And if copper is gaining electrons, right, it's going to be producing the sulfate anion. And if this guy is losing electrons, the sulfate anion will go to it.
Right, right. Yes.
Yeah. And since this guy is gaining electrons, the zinc cation will go to it.
Mhm.
So that entire thing is basically, so I wrote cathodes have positive cores, so electrons travel to them as the current flows. Anodes
Mhm.
negative, blah blah blah. The salt bridge permits anion flow in the opposite direction of the electron flow. It completes the circuit
For sure.
because you can't. Yeah, you need like a complete circuit.
Mhm. Okay, makes sense. Um, I think that's pretty much everything for today, I think.
Okay, so I'm just going to like show you these and then share them with you. So let's see like what you would want. So this one is not really useful. Okay, so this content one, I have a lot of stuff here. So I'm going. Oh, and then this is where I talk about organic chemistry, like electrophiles, nucleophiles, nucleophilicity, and how it's not necessarily the same as basicity. So, and then here, oh, like some biochem stuff, electrochemistry, solubility, hybridization, bonding, some biochem stuff. So I'll share that with you. This over here. Oh, you know what? I didn't even send you like my Anki cards.
Oh my God. I have way too many occupiers. I think I'm good.
Okay, but I'm gonna send them anyway, just because I have like, because the entire point of Anki card is not to have that many. You don't want like an Anki deck with 1,000 cards. Um,
Well, yeah, okay, yes, send it to me, but yeah, I'll use it, but I'm not like a firm believer in Anki, I guess. Is
oh yeah, um, like
like
two people won Jeopardy by using Anki. So, but like I have things that are gonna be like a little different because I can like boil things down. Like for instance, here are some examples of
mm-hmm.
things that are are formed. Here are some like other stuff. Um, what? Oh, and then the math ones also. But oh, did I show you this? This is like kind of like metabolism.
I have one too. I have like a giant one of like every metabolism possible.
Yeah, and like so like the important part is to like know why things happen, like why
Or
the like tell me, like, why does like this irreversible step?
Right.
Why? Why is it irreversible?
Because you need to trap the glucose to not leave the cell, so you phosphorylate it.
And phosphorylating it does what?
It just traps the glucose in the cell.
Yeah, but how?
Pardon?
But how?
How? You just phosphorylate it. So like you put a phosphate group with the oxygen.
So why would the phosphate group make it so it can't leave the cell?
So that it becomes negatively charged.
Yes.
Okay. There.
And in order to pass through the cell membrane,
it's too ionic. It can't pass.
Good. So think about it. Yeah, think about it that way. Because no need to memorize all that stuff. Like, but yeah, if you know the why, like you can deduce like the how. It's also useful to think of things in ratios. So okay, that, and then I have like the brain dump thing. Why is this so slow? Okay. Wait, and how are you doing with cars? Oh yeah, see, this is why like the kinematic stuff is so like useless, because like look, this is like a kinematics equation, right?
Mm-hmm.
But look, it's literally just the definition of acceleration. You subtract v naught on both sides, or v initial, and you divide by delta t. That's change in velocity over change in time, so that's just acceleration.
Yeah, that's how I see it too.
Yeah. And then this is some stuff with springs and pendulums, but we'll come to that when we need to. How are you doing with cars? Because that's at first what you wanted to work with or work on.
Honestly, it's hard to tell because I've been trying to do like the AMC questions again, and I've been trying to do like, let's say 3 to 4 passages in one sitting, and just to see how I do. And I do okay, like honestly, not horrible. But I also think it's because I already did the questions before, and so it's not a fair like assessment. But then, so I've been also doing Jack Weston because he has like daily passages. So I just do those so his questions are like not the best. I wouldn't say like the questions that he made are good, but I think the passages in terms of like the variety is good for me to like check my comprehension of the passage. I think is good.
Yeah, but like I want us to work on like passages together so we can like kind of see like, so I can like see like in like you like using like specific things like in action.
Yeah.
Like, so I can share this with you. Like I say, like first paragraph mostly useless. Group long sentences together into short meaningful phrases. Keep note of the structure. Like what type of literary critic? Formalist, remember?
Yeah, formalist.
Okay. Yeah. So, when reading the question stem, be able to know or find quickly where in the passage the relevant information is. Yeah, reading for structure. That means basically each sentence can be marked as important or fluff in your mind. Let's see. A lot of things are just filler, basically. But you gotta practice so much that it becomes automatic to you. Most important sentences. So those are the ones where a new idea is introduced. This is basically like main idea, secondary points, what tone, the things that are backed by evidence. So make note of the following when two things are compared or contrasted, when a new idea is introduced, when a strong statement is provided without any evidence. I say practice this. For each paragraph, write down or be able to summarize it in like 1 or 2 words. and see if you can do that in your head. Um, yeah, I'll show you. I'll like share that with you. But like, for instance, like this thing over here. Whoops. Yeah, like this over here.
Mm-hmm.
So, um, it'll take practice, but like, so okay, like next time I want us to do at least like a few cars passages together,
Okay.
because I want to see you like do it like in front of me and see like what the overall like what's basically saying
Yeah.
what it's basically saying, like to be able to digest it like at once um without it just being so much information like overload.
Mm-hmm.
Like so like you can like look at this, like I just wrote my summary, which is although the Greeks didn't treat their gods as a religion, they treated them as myths. They did treat divine saviors as religion. And then
Mm-hmm.
here's another one which is talking about some art stuff. So yeah, so next time, like, yeah, I want us, because that's the section that you said that you needed the most improvement on.
Yeah.
And like I know that you've done like all of the passages from the AAMC, and now you're starting passages from like Jack Weston, but like yeah, I want us to like really like like when we go over like a couple of them to for you to really really like understand. Okay? Because
Yeah. Yeah. No.
I'm never like a fan of the approach where you just do more. I think you can do so much with less if you really really like kind of like understand it. So yeah, so I'll share some stuff with you. But yeah, how is that like next step test?
Uh, which one?
Oh, like the one that you like, this one over here.
Oh, this one is it's fine.
It's fine.
Yeah. Yeah, I mean, I didn't, so I did it without, I didn't really review before I took that test, and it, like,
You didn't
some
what?
things I forgot, but,
You didn't what?
so I didn't review before taking this test,
Mm-hmm.
so I kind of forgot some things, but this week I've been just, like, reviewing more, like,
Okay.
yeah.
Um. Yeah, I think I have like a video on my YouTube where I go over like like a section and I just like talk out loud about the way that I like go about it. I think it might be, this is me like building a computer, but let's see. I don't know. It could be this walkthrough. Um, but yeah, there's like yeah, I'll like send you the link or whatever. But I think I like go through one, and I just like kind of think out loud, about like how I would like go about it.
Okay,
So yeah, okay.
that sounds good. Let's see. So I think, so on Saturday, I'm gonna do another, like, practice exam, so next week we can do more, like, questions. But I
Mm-hmm.
think between now and when I take the test, we can do cars.
Mm-hmm.
So
Like just cars, or like stuff from like the next another next step test.
no, just like cars, like go over cars in like more detail.
Okay.
Yeah.
And you're going to send your, I guess you'll send them to me or whatever.
Um, or we can just like do it on the spot without me doing it first.
Okay. Yeah, we could do that. Cuz yeah, I basically, want you to get to the point where you're not at the mercy of getting a hard passage or not. Like, it's just like a really good skill to start to have, I suppose.
Mm-hmm.
Because everything is like passage based, so I guess that's why they place such a high emphasis on cars.
Mm-hmm. Mm-hmm. Okay, sounds good. Yeah. So I'm free on Friday, except for like in the afternoon. Well, yeah. So.
Um, well, your afternoon is different from mine, so uh, you know, like my afternoon is like your morning, so you know what I mean.
Yeah, yeah. So what time are you free on Friday?
So when you say afternoon, you mean your afternoon, right?
Yeah.
Okay, so I guess my afternoon. So let's see. I don't know. Does like 1 p.m. work?
Mm,
Noon?
do earlier maybe.
Okay. Um, let's see.
I have to be somewhere at 11 my time, or I have to leave at 11 my time. So
Okay, you don't have anything after?
no, I do have. So I have something from my 11 to
Okay.
3:30.
Um, okay. So we could possibly do like your 3:30, which I guess is like my 6:30.
Hold on, let me check. Yeah, yeah, that could work. Yeah, that works.
Okay. How far do you think you are from me?
Uh, are you in New York?
Mm-hmm.
How far, like distance wise?
Mm-hmm.
Few thousand miles. I don't know, few thousand kilometers.
Uh,
Few hundred maybe. 500? No, no, that's too little. Let's say 2,000 kilometers.
and how many time zones? Three, right?
Yeah, I think so.
So why don't we say 3,000 miles?
Okay.
Because that would make it 1,000 miles per time zone.
Okay.
How many time zones exist?
In the world?
Mm-hmm.
I have no idea. I honestly have no idea. Like 12?
Well, if a time zone there's a certain
24.
time. What's that?
24.
Okay, so if each time zone is 1,000 miles, what would be the circumference of the Earth?
I have no idea.
Well, think about it. 24 time zones. Each time zone is 1,000 miles.
So like 24,000.
All right, now look it up on Google. See what you get.
Wait, what? The circumference?
Yeah, of the Earth.
40.
Hmm.
Yeah, 40K.
Oh no.
Kilometers.
Oh, I mean in miles.
Well, I don't do miles, so I don't know.
Oh, just like look it up.
Oh, 24 miles.
24,000, right?
Yeah.
So you see how we got that?
Mm-hmm.
Anyway, that's just the last thing. Okay, so yeah, I'll
Cool.
see. I'll see you on, yeah, Friday. Okay.
Okay, yeah, sounds good.
All right. Take care.
Thanks. Thanks. Bye.
No problem. All right. Bye.